In this second video, I'm going to talk about the theoretical and experimental tools we use to ask the question that I brought up in the first video. And remember, that question is this: how does communication shape belief accuracy? So in order to think about this question, we've adopted a model developed by Maurice de Groot in 1974. Now, de Groot wasn't studying beliefs with regard to accuracy per se. He was just studying opinions more generally. But we can use this model to think through it and infer how group dynamics might shape belief accuracy. So the model de Groot studied is very simple. He assumes that everybody starts with some initial independent answer. This is our collected intelligence baseline. De Groot then assumes that people observe the beliefs of their peers. So that could be everybody in the group, or maybe just a small subsection connected to them in their social network. And after observing the beliefs of their peers, we assume that people then revise their beliefs to become more similar to their peers. And this is the only real assumption of the model, that people become more similar over time. But it's an assumption that's been shown time and again in literature on social psychology. For example, you may be familiar with the famous Asch conformity study that showed that people were driven by conformity pressures even when the group was clearly incorrect. Now, de Groot's model is an iterated process, which means that after everybody's revised their answers, people are then able to observe the revised answers of their peers, to then adjust and revise again, and then rinse and repeat and so forth. The idea being that this models what's happening maybe in a conversation. I have a belief, I learn what you think, I adjust, you adjust, I adjust your adjustments, and so forth. So what de Groot did was he studied this model mathematically to try to understand group belief formation. So the first result he gives us is that if you repeat this process indefinitely or infinitely, groups will asymptotically converge on a single shared consensus belief. Now, you may not find it empirically plausible that groups converge on a shared consensus belief, but the idea is that we can use the asymptotic properties of this model to think through the direction in which group beliefs are going. Now, the second result de Groot gives us is that this consensus belief is equal to a weighted sum of everybody's initial independent beliefs and their centrality in the social network. And this is what's going to be most important to me as I start to think through how group dynamics shape belief accuracy. The most important thing that we need to pay attention to is any factor that can determine who's more central or who's more influential. Now, if you're not familiar with social network theory, which many of you probably aren't, the easiest way to think about centrality is in terms of how many friends I have. The more friends I have, the more people will observe my belief, and the more I will contribute to that group consensus. It's actually quite intuitive. Popular people are more influential. And that's the type of centrality I'm going to be focusing on in this video. But I want to acknowledge that there's a second way of becoming central. Instead of having a lot of friends, maybe I just have a few friends, but I'm really influential on those few friends. In that case, if we have a group, even where people are all equally connected, maybe we're sitting around a table and everybody can see everybody, some people might still be more central or more influential. So in the next video, I'm going to talk about how we can use the model and the results that I developed in this video to think through more complex types of organizational and decision-making processes. Now, since network centrality is a really important thing in determining group beliefs, that tells us that the only thing that matters in terms of groups is their network structure and whether or not it creates a network where some people are more central than others. So here's a diagram that illustrates this concept. On the left-hand side, we have what we call a fully decentralized network. This is a network where everybody is equally connected. Now, the de Groot model tells us that in a decentralized network, everybody will simply converge on the simple initial estimate, the average of initial estimates, the unweighted sum. Now, this seemingly simple result is actually really exciting from a collective intelligence perspective, because it tells us that if people are embedded in decentralized networks, then social influence isn't a good or a bad thing. It means that groups should be able to preserve the wisdom of crowds even as their individual members become more similar. Now, as we move to the right on this figure here, we see increasingly centralized networks, and visually what that looks like is that the network is more and more dominated by a small number of central nodes until you get to the one on the right, where you have one central node that observes everybody and a lot of peripheral nodes that observe that central node. Now, as we move to the right, de Groot tells us, and it's really quite intuitive, that when you have dominant people in a network, those people, by and large, will determine group outcomes, which means instead of getting the wisdom of the crowds, you're getting the wisdom of the few. Now, one of the cool features of the wisdom of crowds as a statistical property is that it tells us that the crowd estimate is guaranteed mathematically to be more likely than a randomly selected individual, which means that in these networks dominated by a few people, since we're getting the wisdom of the few and not the wisdom of crowds, we're going to lose all of those statistical benefits associated with the wisdom of crowds. So the idea is that if we have some intuitive sense or even theoretically motivated belief that social influence is a bad thing, that it leads to hurting, we should expect to observe it in highly centralized networks and not in decentralized networks. So the first thing that I want to do, and that's what's going to be the rest of this video, is talk briefly about an experiment designed to test this idea. So what we did very briefly is we use an experimental paradigm that has people come from around the web. So we're doing this online. We set up a website that has people complete estimation tasks. So you see an image of a jar of M&Ms here, and we ask how many M&Ms are in the jar. Or you see a meal in the center, and we'll ask them things like how many calories are in the meal. Or we'll show a basket of consumer goods and ask people to estimate how much do you think this basket of goods costs. And that's what we're doing. We're having people complete these estimates. And the basic paradigm is that we first have them provide their initial independent answer, our collected intelligence, wisdom of crowds baseline. We then let them interact with people who are also participating in the experiment. We let them observe their answers. We're doing this all in real time. We then get a final estimate from people, and all we do is we take the average estimate at the beginning and the average estimate at the end, and we say which one is more accurate. And that lets us compare independent estimates with collectively produced estimates. So what we do is we have hundreds of people come into our website all at once, and we randomly assign them to a few different experimental conditions. On the left-hand side here, you see our social conditions. We build online social networks where people are all participating simultaneously. We create one network that's a decentralized network where everybody's equally connected, and one network that's a centralized network that has one really influential person and everybody's peripheral. The idea is that we're going to compare these two networks. And from the individual's perspective, the website that they're looking at is exactly the same. They have no way of knowing which condition they're in, which tells us that if there's some difference between these conditions, it's happening behind the scenes due to the structure of information flow. Now, we also want to be sure that what we're observing is really driven by social influence and not just the fact that people are revising their answers multiple times. So we also run this control condition with no social information where people just answer the question over and over again. All right, so very briefly, what we find from this experiment, well, it's exactly as you'd expect. In the centralized networks, group beliefs are determined by the central node. If the central node has a belief that's really high, the group goes up. If the central node has a belief that's really low, the group goes down. Which also means if the central node has a belief that pulls the group in the right direction, the group becomes more accurate. If they have a belief that pulls the group in the wrong direction, the group becomes less accurate. Now, remember, for decentralized networks, what we expected to find is that people would simply converge on the average answer. There would be no change in the wisdom of crowds. But what we actually found was that groups in these decentralized networks became reliably more accurate as a result of exchanging information. Now, this is completely contradictory to our theoretical expectation. So we had to kind of go back to the drawing board and think, what could create these results? Which is why it's really valuable to have a formal model. Because a formal model helps us to think through, why do we expect to get what we expect? So what we did was we actually went to each person in each group and said, how much did you revise your answer? So you've got your belief over here, you've got the peer belief that you're observing. Are you closing the distance halfway? Are you completely adopting the peer belief? Are you standing your ground, right? And what we're looking for is any pattern that impacts how people move. And as it turns out, people who are more accurate make smaller adjustments. People who are less accurate make larger adjustments. So people who are accurate are basically stubborn. We see this accuracy stubbornness correlation, or you can think of it as an error adjustment correlation. The larger the error, the larger the adjustment. And when we went back and we fed this into our theoretical model, and it turned out to be sufficient to explain our results. And what we did was we went and looked at our study, and we took each question by each group. We measured the error adjustment correlation. We measured the change in error, and lo and behold, we see this pattern here. What you see here is that the groups in the lower right-hand corner, they show the largest error adjustment correlation. Remember, you can think of that as an accuracy stubbornness correlation. They also show the largest decrease in error. So in this plot, down is good. Down means a decrease in error. Now, in contrast, the groups in the upper left-hand corner show a negative error adjustment. So here, the incorrect people are really standing the ground, and those are the groups that show an increase in error. Now, by and large, what we see is that on average, there is a positive error adjustment correlation, which is what produces the results. Now, this is usually the point at which someone would raise their hand and say, yeah, but Josh, this is all well and good for questions about, counting gumballs in a jar. But what if I want to ask something that's really important, where people's beliefs are shaped by cognitive biases, right? A huge problem in management and decision making. So what we did was we went and we ran this study again, but we asked people political questions. And I don't want to get too far into that study. You can go read about that. That's a conversation for another day. But very briefly, what we find is that collective intelligence can even overcome cognitive biases. Now, I'm not going to stand here and tell you that group information exchange will always improve belief accuracy. Remember, we had these groups in the upper left hand who showed a negative error adjustment correlation, and they got worse. However, what we see by and large is that across many repeated trials and even different types of questions like political questions, we still see this main effect. Now, when we start to put this together, what we start to get are some of the first contingencies of our contingency theory of collective intelligence. So the first contingency is that group intelligence is contingent on a positive accuracy adjustment correlation, which means the people who are in your group that are experts or that are accurate, they need to know they're accurate. A second contingency is that collective intelligence is contingent on group structure. So we're studying these simple lab structures, but you can think about how patterns of information exchange, who communicates with whom, shape everything from our friendship networks to our organizational and employment networks to our democratic networks. So as you start to design processes to improve group decision making, we can start to put some of these ideas together into coherent strategies. So one clear strategy is that you want to encourage self-assessment. You want to try to facilitate the production of a positive error adjustment correlation. A second key strategy is that you want to promote collaborative structures. So remember, the network idea here is that you want people to be equally influential on group decisions. So whether that's literally structuring who talks to whom, or thinking about how your communication styles in the group or organization shape influence, you want to promote collaborative structures. Now, I started this talk with a bit of a paradox. We had these different studies that came to different conclusions, and we've started to produce some contingencies that show why groups will sometimes get better and sometimes get worse, but we haven't really started to figure out why different processes like numeric exchange or unstructured discussion will produce different outcomes. That's what I'm going to talk about in the next video.